Okay, so you've got your assignment is out, and due at the end of the week, like usual. Any questions or problems before we go any further? Yeah.
Is it possible for you to go over a little bit how over the decision tree for merge sort, how to get started with that?
Okay. So there's a problem which is to it asks some questions about the decision tree for merge sort. So what is sure that's working. What is a decision tree? What do we use decision trees for? Yeah.
All possible directions of using a sorting algorithm on some
Okay.
function.
So we said all possible directions for using a sorting algorithm on something. So the idea is we use a decision tree to characterize all the comparisons that a sorting algorithm might do. And so we, for any sorting algorithm, if I say you've got an array of length 10, you should be able to say which two elements are compared first. So if it's selection sort, what are the two elements that are compared first? First and the second. And for insertion sort, it's also the first and the second. Turns out for merge sort, I guess it'll probably be the first and the second. But it's not always the first and the second. And so the tree encodes, at the root of the decision tree, that corresponds to the first comparison done by a sorting algorithm. And that result of that comparison is either yes or no. If it's yes, then there's some other comparison that's done next. If it's no, there's some other comparison that's done next. Excuse me. And so the tree encodes all that stuff. So if you look at a single path, a single branch in a comparison tree, what are you looking at? Each node you're going through in the tree corresponds to some comparison. What does the whole path correspond to? Yeah?
One possible iteration of that.
Yeah, one possible outcome of the sort. So you start at the root, and let's say you do a sequence of comparisons. It's yes, no, yes, 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 no, yes, no, and you're at the root. Well, you've done it. You've sorted the array by doing the comparisons on that path. So every single possible sequence of comparisons that can occur when sorting an array shows up as a path in that tree, and vice versa. So what does the length of a path tell you? Yeah?
How quickly it can be sorted?
Well, the length of a particular path tells you, yeah,
How many comparisons were done?
how many comparisons were done when that outcome happened. So a really long path, the longest path in the decision tree, corresponds to the worst case for that algorithm. And the shortest path corresponds to the shortest path for that the best case for that algorithm. Okay? So when I ask you a question like, what is the length of the longest path in the decision tree for merge sort? Does that require you to draw a decision tree for merge sort? What's it require you to know? What am I asking when I ask you a question about the longest path in the decision tree for merge sort? Yeah?
Big O?
Well, more precisely, yeah?
How many comparisons?
Yeah, I'm asking what happens how many comparisons are done in the worst case? If I ask you about the shortest path, I'm asking you about the best case. If I ask you about the average depth of a decision tree, what am I asking you about?
The average case?
Yeah, the average case. So don't waste a lot of time. It might be a useful exercise to draw a decision tree for very small arrays, but after that it becomes just a burden. So just be able to relate questions about decision trees to questions about the algorithm itself. Any other questions? Anything else? Okay, the caddis problem this week. What algorithm is it about? if anyone's looked at it. Yeah.
Breadth
Breadth.
strong components.
Well, just breadth first search. Yep. All it is basically an implementation of breadth first search with a particular form of output that I want. And you know this for two reasons. One reason is we talked about breadth first search last week. What's the other reason? Yes?
Because you have to return everyone at a certain level.
Well, that's another reason. You got to return everyone at a certain level. What's the third reason? Yeah.
Shortest path?
No. What's the name? Okay, so if you've read the Caddis problem, what's the name of the school where the rumors fly around? Yeah?
Initials are breadth first search.
It's the Benjamin Franklin School. And where's the school located? Broken Fork, Saskatchewan. So I left you a clue. I just wanted to make sure you appreciated it. Okay. Okay, so last time we talked about breadth first search. And breadth first search is a way to find the shortest path between a starting vertex and every other vertex. Or think of another way, the distance between any new pair of vertices from a starting vertex to any other vertex in an unweighted graph. But now we're going to add weights. So this is the same basic graph we were using for breadth first search examples, but now I've added weights to the edges. And so that changes the game. Now the shortest path, like what's the shortest path from A to, let's get one where it's different. Oh well. What's the distance from A to F?
0.
Not, distance from A to F is not 0 here.
Well, there is a path. It's 0.
Oh, I'm sorry. Yeah, you're right. I forgot. I didn't see the -5. Okay. So if we go directly from A to F, that's 4. But as someone just observed, if we go from A to B to C to G to F, that's a path of length 0. So that path, which contained 4 edges, is less cost than the one that went directly. So we have to pay attention to the weights. Breadth first search won't do anymore. So let's see how to do that. Now, we're going to make an assumption in all the algorithms you look at for solving this problem that there are no cycles of net negative cost. So what is a cycle of net negative cost? What's that sound like? Yeah.
Just the whole pathway around that will not result in the full path equaling something negative.
Okay, so we don't want any cycle of to be negative. Now, does this thing have a cycle of net negative cost? Is there any cycle we can go around and get? The closest one would be the cycle CGF, but it's going around that loop is positive 1, so that's not negative. So what I've just highlighted here is the shortest paths tree for that graph right there. So the yellow edges show you in code, it's a tree first of all, just like a breadth first search tree. This is shortest path tree. And it shows you the shortest way to get from A to E is not directly, but to go A, B, C, G, F, E for a total weight of 1. So just like you can encode trees in breadth first search, you can encode trees like that in shortest paths. And so here is the actual array representation, and you'll see we've got over here previous, just like for breadth first search. So it says the previous of B in the tree is A, the previous of D is C, and so on. So that encodes the yellow edges. And this other array, distance, encodes the actual distance. So the distance from the start, which is A, to say E, is 1. It's the same idea that we used with breadth first search, the same 2 arrays. Before I go on, why do we need to make this assumption about known net negative cost? Yeah?
Because if there's a net negative loop, you can just travel through it an infinite number of times and get negative.
Right. The problem with a negative loop, make this be a negative 7, let's say. This edge from G to F. So now you can go C, G, F, C, G, F, C, G, F, and that's negative. So now what's the shortest path from A to E? Is it A, B, C, G, F, E? That'd be a link 1, but if we went A, B, C, G, F, C, G, F, E, that would make it lower, right? If we go around that loop again, that'd make it lower still, because every time we go around that loop, we get a negative 1. So there is no shortest path from A to E. At least no finite shortest path from A to E. So the problem isn't very well defined when there's a negative cycle. So we're going to assume for all of our algorithms that there's no negative cycle. The fundamental operation that we're going to use, we're going to look at 3 different algorithms for finding the shortest paths under different assumptions. And it's the update operation. And the update operation applies to an edge. So here is the update operation. So to update an edge that goes from U to V with weight W, what we do is we compare the distance to V. So there'll be a distance array and a previous array. So we compare the distance of V, the distance to V to the distance of U plus W. And if the distance to V is greater than distance of U plus W, we update distance in previous as shown here. The new value of distance of V becomes distance of U plus W, and the new value of previous of V becomes U. So what's the intuition behind the update operation? What you should imagine is that you're in the middle of an algorithm, you've computed, you've got an approximation to the distance of V. So you've got maybe some computed distance to V that's the best you've seen so far. What would it mean at that point if you discovered that the best known distance to V is greater than the best known distance to U plus W? What is that saying?
This is a shorter
Yeah.
path through. Yeah, I think there's a shorter path through.
Right, now you found a better way to get to V. So there was some other way to get to V before. Remember, there's a start. So there was some way to get from the start to V. Now you found that if you go from the start to U, and then go directly to V from there, that's cheaper than whatever path you found before. So you found a better way via U. And so you update the 2 data structures. Distance of V becomes that shorter distance that you just discovered. And the previous of V, the parent of V in the tree, becomes U, because you're coming to V through U now. So that's the update operation. And all 3 algorithms that we're going to look at use the update operation. They differ in how they decide when and where to update edges. They all work by updating edges. And that's what I just said there. So let's try out the update operation here. What will happen when we update? Well, let me stop. All our algorithms will start in this state. You've got a graph, you've got a previous array that's full of nulls, and you have a distance array that's full of infinities, except for the start vertex, which will have a distance of 0, because it's always 0 from a vertex to its, from a start vertex to itself. So what will happen? What will change about our data structure when we update the edge from A to F? Okay, what's the current? So V is going to be F, U is going to be A, W is going to be 4. What is the current known distance to F? Infinity. And what's the current known distance to A? 0 plus the 4. So infinity is greater than 4. So we found a better way to F. So we're going to update. And what's going to change about our data structure when we update that edge? Okay, so it'll change for F. So F's previous will become A, and its distance will become 4. So you see it change there. So we update that edge, and now we've improved our 2 arrays. Right? Now, what about CG2? Currently, the shortest path we know to G is of length infinity, because we don't know a path. And currently, the shortest path to C is infinity as well. So what's going to happen when we try to update that edge? Is anything going to change or no? Well, distance of v is infinity. Is infinity greater than infinity plus 2? No, they're the same. So no update happens. So you can try to update an edge and nothing's going to change if that doesn't give you a better way. What about FE1? We're going to update the edge F to E that has weight 1. Is that a cheaper way to get to E?
Yep.
Okay? Because the current way is infinite, and we currently know how to get to F in 4, plus 1 gives 5. So we're going to update it. E becomes, should have a parent of F and a distance of 5. And it does. And then finally, AE3. Notice we're updating an edge into the same vertex we did before. We updated an edge into E here. Now in step 4, we're updating an edge into E again. Is anything going to change?
Yeah.
Well, let's see. E has a distance of 5. And currently the distance to A is 0. And you got an edge of weight 3. So that's a way to get to vertex E in 3, which is better. And so we'll change E now to have a new parent and a new distance, because we found a better way. Right? So there's 4 examples of applying the update operation. So you need to get comfortable with the update operation, because that's just our bread and butter. Any questions I could answer about it? Yeah?
This is more good implementation. How do you tend to deal with infinity? Would you treat it like
Okay.
a case if you're storing an array of integers? Is there
Okay, so that's a great question, and some people ran afoul of this last week on the caddis problem. So the tempting thing is to say, okay, our distances are going to be integers, and so I'm going to make the max int, the max positive int, stand for infinity. So what could go wrong if you do that? Yeah,
If you add to the max positive int, it overflows.
right. If you add even 1 to the max positive int, you got a negative number, unless you're in pi 5. So, in fact, up here, think of what would happen. Suppose distance of v and distance of u both contained infinity, i.e. max int. And you're comparing distance of v, which is infinity, to distance of u, which is infinity, plus w. Well, before we said that was a tie. Infinity plus something is still infinity. But what's going to happen in this case if you take infinity and compare it to infinity plus 3 or whatever? It's going to become negative. And we're going to store that negative number as a distance to v, which you don't want to do. So, what do you do? Yeah.
Does it work to set it to like the max integer divided by 2 or minus?
Okay, so you might consider using something a little smaller than negative infinity. I mean, than max int. But how much smaller is safe, right? So, on the caddis problem, the thing to have done would be to notice that the maximum toll for a city was 10,000, and the maximum number of cities in a graph was 2,000. So that meant the longest possible path could have a toll of 20 million, I think, is what that worked out to. Or 200 million, I forget. Anyway, you just use something bigger than that. So you sort of can use the specification of the problem to figure out what's an impossibly large number, a number you won't reach anyway. Or you could just, you could use max int, and you could just, when you did the comparison, you just have to be careful. You can't just do the addition and compare. You have to check and make sure that you don't make the max int wrap around. You need to be aware of it. Once you're aware of it, it's not a problem anymore. Yeah?
Is it possible to use like a negative number?
You could use a negative number, sure, if there's no, I mean, it's possible for there to be negative paths of negative length without having negative cycles. So you have to be careful about that. I mean, imagine a graph with 2 vertices and 1 negative edge. The path from one to the other is going to be negative, even though there are no cycles. And if you do, again, you're special casing it. You've got to say, if it's negative, do this. So it's kind of annoying. another thing you could make, if you think positive maxent is safe, you could use maxent but store it in the long. And then the long isn't going to overflow. You just got to make sure your maxent, your infinity is bigger than any number that you would get as the length of the path normally. Any other questions? Okay, so it turns out there are a couple facts about updating. One is you can blindly start updating. Updating an edge doesn't ever get you stuck. Either updating an edge is going to do nothing because nothing changes, or it's going to improve things. But it's never going to improve things in a way that keeps you from getting to the actual best solution. And it turns out that if you just randomly generated update operations and did them, and made a list of the updates that you did, the only updates that matter are the ones for the yellow edges. So if you could predict in advance what the yellow edges were going to be, in other words, the actual tree, the shortest paths tree, then there is a perfect order in which to do the updates. So what would be the perfect order? So you start with all these, with the initial value here, and I tell you which edges are in the ultimate, which edges you're ultimately going to find as the shortest path tree. In what order should you do the updates? Should you start by updating the edge from D to H? No, that would it wouldn't do anything because everything, the distance to D, the distance to H are both infinity. What edge should you do first? You do A to B. And when you did that, you find out that the distance from A to B is 2. Then what would you do? B to C. And then you could do either C to G or C to D. So you sort of do them in order. You want to make sure that you've done the edge into a vertex before you do the edge out of it. Now, that's true, but why is that not a practical algorithm? No, you don't know in advance what the tree is. That's what you're trying to find out. But the point is, if you do a whole slew of updates, and it turns out that in addition to all the other updates that you did, somewhere as a subsequence of the updates that you did do, you've got the yellow edges in the right order, then your algorithm is going to be correct. So you can waste all the time you want updating things as long as you update those yellow edges in the right order at some point. So let's just try it out. Let's try the edges in this order. So if we do AB, we get distance from A to 2. We do BC, we get 3. We do CD, we get 4. We do D to H, that's 5. We do C to G now, that's going to be, what, 5? We do G to F, 0, and then we do F to E. So those are the only 7 edges that need to be updated. And if we had interspersed other updates, then we could stick any number of updates before the AB, any number between the AB and the BC, any number in here. It would take longer, but we'd get to the same result because it has these updates as a subsequence. So any algorithm that can manage to guarantee that the edges that count are evaluated in a proper order is going to be correct. So that leads us to our first algorithm, the Bellman-Ford algorithm. And it'll work on any graph as long as there's not a cycle of net negative cost. And it's brute force. So if you've got to guarantee, all you know is the starting vertex, A. What's one way, and some edge, there's some yellow edge that needs to be updated first. What's the simplest way you can think of to make sure that the proper edge gets updated? Yeah.
Update all of the edges that come out of it.
Well, yeah, so that is even a more special case than Bellman-Ford actually does. But yeah, we could start by updating all the edges out of A, but then what would you do? Then we don't know what the next edge you should do.
Yeah.
What should be, how can you be sure? If you need to be sure that some edge, you don't know what it is, there's some edge that needs to be updated next, you don't know what it is. How can you make sure that it gets updated? Yeah.
Choose the smallest one.
Well, that smallest one may not be right. Yeah?
So why would we not do breadth first?
it's not enough to do every edge. You've got to do, it depends on, you gotta do them in the right order. Right? So breadth first isn't necessarily gonna work. We've gotta do A to B first, but what edge do we want to do next, did I decide? B to C. No, that's not gonna be next in a breadth first search. Yeah.
Can you just iterate through all?
Right, do them all. That's what Bellman-Ford does. It updates every single edge. That guarantees that you're probably going to waste a lot of time updating edges that don't need to be updated, but it does guarantee that AB gets updated. What do you do? Do them all again. And whatever else happens, BC will be updated. So now you've updated AB, and later you've updated BC. Do it again. Now CD will be updated. First pass we did AB guaranteed, second pass we did BC guaranteed, third pass we did CD guaranteed, and we keep doing that. And how many times do we have to do that before we're guaranteed that we've evaluated each edge in the right order? Yeah?
Just the number of edges in the graph.
That's the number of edges in the graph. So in this case, there are, what are those? Not number of edges in the graph, number of edges in the tree. All right, so each iteration we're guaranteed to deal with at least one update in the right order. So in this one, there's what? 11? 9? There's 9 vertices, so the longest possible path will be 8. As it turns out, we never do get to I, so the longest possible path is going to be 7. So Bellman-Ford just updates, V minus 1 times. And then it stops. And it's guaranteed to have done everything at the right time. So we can't tell, we're going to update them all. Now, could you get lucky? Think about that first update that updates every edge. Could you be lucky and end up in that first pass updating AB and then later BC and then later CD and then later DH and so on? Yeah, you might get lucky. Okay? But you can't get, you have to at least do AB in the first pass. Okay? Now, you're probably sitting there saying, well, you're guaranteed to do BC and CD and DH in the first pass as well, but what's the problem? Right. It doesn't do you any good to do BC unless you've already done AB. So the first pass, you're guaranteed to get one of these edges right. Second pass, you're guaranteed to get the second one right, and so on. All right. Now, there's our algorithm. It just consists of this. For each edge, you initialize the data structure. You set all the distances to infinity, all the previous's to null. You set distance of S to 0. Then, V minus 1 times, you update every edge. So, I said it was brute force. That doesn't look very efficient. Can you think of a way to make it more efficient? Think about the times you get lucky with the first update or the second update. Yeah?
You could break out the loop once you notice that an entire pass hasn't made any changes.
That's it. So you make the first pass, and if you were lucky, you updated every edge in the perfect order. And what that means is you have found the shortest path tree. You don't know it yet, but you found the shortest path tree. The next time through, you're going to update every edge, and if you notice that nothing changes, nothing about the tree changes, none of the update operations change either array, there's no point continuing because you found the solution. So if you do a pass where nothing changes anymore, you can quit. Or if you do V minus 1 passes, you can quit. Either one, you're at the end. Yeah.
Could you sort them in a priority queue based on the number of edges coming in, and then always evaluate the ones with like all the edges coming in have been evaluated first?
Right. So you could do some sort of pre-processing. For example, you definitely want to do, you would want to do the edges out of the start vertex. That's sort of a no-brainer to do them first. And so you're proposing a heuristic, really. It's not guaranteed to win all the time.
Well, I was saying like you check the edges coming in and see if they've been evaluated, and you always in your priority queue say the ones that have all their edges coming in have already been evaluated, then you do it.
That's sounding suspiciously like a DAG algorithm. But the problem is it's not a DAG, it has cycles. So there'll be situations where there is no vertex for which you've looked at every edge coming in because they're involved in a cycle. So that'd be the problem with that. we'll actually look at one of the algorithms we'll look at runs on DAGs. It does something like that. Next actually does exactly that. Okay? So it's simple. It just does the update operation until it's done enough or until things stop changing. And it hinges on the fact that doing an unnecessary update operation only wastes time. It doesn't prevent you from finding the ultimate solution. Any other questions about Bellman-Ford? Well, let's look at there's the optimization. Let's look at the analysis. So what's the complexity of that first initialization block? Filling in the distance in previous arrays. Right, that's just O of V. And then what about the body of the loop? So the outer loop runs V minus 1 times, but what's the cost of this, just the for each loop? Now, how many edges get updated in that for each loop? All of them, which is E. So it's O of E for the update operations, and then this finding all the edges is whatever, depends on the data structure. So it's the cost of enumerating the edges in whatever data structure you're using. And so the body of the loop is the cost of enumerating plus the cost of the updates, but you do on the order of V of those for each loops. So we get that. We get O of V for the initialization, O of V times enum for the outer, for enumerating the edges, and O of V times E for the updates. Now, what about this second term? We could actually make that smaller. Do we really need to enumerate all the edges every time? You can enumerate them once and save them, and just reuse them. So that would just become O of enum if you did that optimization. You only need to do it once. But that's not the dominant term anyway. Well, I guess it is a dominant term. The way I've written it is. So we got O of V times enum, and for a matrix, that's O of V cubed. And for a list, it's O of V squared plus VE. So it would change slightly if we did the optimization, but so it's far from being linear. Linear on a JC matrix would be O of V squared. There's an extra V term down here. Linear down here would be V plus E. There's another V term down here. So not a very efficient algorithm, but it will work in any situation where the problem is well defined. Namely, there's no cycles of negative cost. Okay. Now, let's think about if we've got a DAG. So I changed the graph. So that edge from C, that used to be an edge from F to C, now it goes the other way. So now this thing is actually a DAG, no cycles. And we want to do it again. What we're looking at is a more clever way to do the updates so that we don't have to blindly do them over and over again like we did in Bellman-Ford. But we still got to arrange to do them in the magic order. So, you have a DAG algorithm to design. What should you do? Yeah.
Could you sort them in topological order?
Okay.
And then use your update from,
Yeah.
doesn't, I don't think it would matter where you start with the update.
Well, we want to do a topological sort. It's a DAG algorithm, so you do topological sort. And then you start doing update operations in topological order. So in this case, our start vertex is A. So it really wouldn't matter, if there's some edges, if some vertices that come before A in topological order, they don't really matter. You could process them, but they're not going to be part of the tree because they're not reachable from A. So you would start at A, you update all the edges out of A. That would get that edge from A to B done. Then you would update all the edges out of what? What would come next? In a topological sort. What would come after A? B. So you do all the edges out of B, which would get that edge from B to C, is the one that really matters. So now you've done A, B, and B, C in that order. The next one in topological order is C. So you do all the edges out of C. Then you can either do D or F and so on. But by doing it in topological order, you just have to make one pass, and you're guaranteed to get all the yellow edges in the right order. Yeah?
Does the topological order follow weights?
Topological order ignores the weights. The topological sort just pays attention to the structure of the DAG. You know, you're sorting from sources to sinks. So you start with the sources. So you deal with all the vertices that lead into you before you deal with yourself. Before you can deal with F, you've got to deal with B, C, and G. And that's what topological sort does for you. So we linearize and then update the edges out of each vertex. So here's one possible linearization. I threw I in just for the heck of it. That could come first. It's a source. So I, A, B, C, and so on. And subject to that ordering, here's a possible order the edges may be considered. So there'll be edges out of I, which don't matter. These edges out of A. Then we do AB. So AB has to come first. Then we do B. BC comes next. Then we do C, and we get CD and CG in some order. It really doesn't matter which order they came in, and so on. So we've got this sequence. Every edge is updated, but we're guaranteed that the yellow edges are updated in the right order because of the topological sort. So that's a huge improvement over Bellman-Ford if you got a DAG. Okay, to linearize it, it's just the cost. It's just the topological sort, linear time. And then what about the updates? How many updates are we doing? E. We're updating each edge once. So we've got to enumerate the edges plus update the edges. So the cost of enumerating dominates. Add it all up, you get the linear time. So it's just proportional to the size of the data structure. Again, it's just updates. But they're done more cleverly here because it's a DAG. Okay, so that's our second algorithm. Any questions about that one? Right, it's just keep in mind both these algorithms. The brute force Bellman-Ford is doing updates all over the place, and ultimately guarantees that if you listed all the edges updated by Bellman-Ford from left to right, you'd be able to identify a subsequence of yellow edges that follow this pattern or something similar. That's why it works. Yeah?
Would you be able to run this on a strongly connected, like on a metagraph?
Sure, you could do, metagraph is a DAG. You know, if you do a strongly connected components algorithm, then you could run this on a DAG. On a metagraph, which is a DAG. Yeah?
This is only going to produce like the previous and distance.
Yes.
And then you would have to, say if you wanted to get from like A to G, you would just have to follow that to get total cost.
Oh, okay, so he's saying it gives you previous and distance. Let's go back where I've got a previous and distance array. Hopefully I'll find one eventually. Okay, there's a previous and distance array. Suppose you wanted to know now the shortest path from A to H. How would you recover it from the distance, from the previous array? You want to know the shortest path from A to H. Not just the length of it, but the actual distance.
You follow each of the previous nodes up to A.
Yeah. So when we go from A to H, we actually start at H. And it says H's predecessor is D, B's is C, C's is B, B's is A, and A's the root. So you've got it backwards. So you turn around and that's the actual path. So there's no, you don't have to do a non-determinate sort. You just go directly from the trick is to start at the end and work your way back. Any other questions? Yeah.
Is there any instance where you'd want to use the Bellman-Ford, as opposed to the next one you showed us?
Okay, so he's asking, when would you use Bellman-Ford as opposed to the one the other one, the DAG algorithm? The answer would be, you can't use the DAG algorithm unless you have a DAG. So if the graph has cycles, you can't use the DAG algorithm.
But when you're linearizing it, doesn't it turn into a DAG or
No, linearizing, you can only linearize a DAG.
Oh,
You can run a strongly connected components algorithm, but that's not going to get you shortest paths. Anything else? Get back to where I was. Okay. So we have looked at, the first assumption was no negative cycles, no net negative cycles. The second one was we were assuming DAGs. The third we're going to look at doesn't allow negative edges. It allows cycles, but it does not allow negative edges. So this is the third one we'll look at. So the Bellman-Ford is as general as it can get. These other two are special case. Let's take a break and we'll look at this third one. Okay, so before we look at this next algorithm, this last one that doesn't allow negative edges, let's think about this restriction we have on no negative cycles. So imagine we replace the 1 here from G to F with a -7 so that you have a negative cycle. what is the, we said that if you do that, then the shortest path from A to E doesn't exist, because you can go around that cycle as many times as you want and get smaller and smaller paths. So we could redefine the problem. We could say, given a graph that has set negative cycles, I want to find the shortest path that does not take a cycle. So you could talk about the shortest path from A to E that does not involve a cycle. Right? That would be more general, a different way of describing the problem. And it's a problem that's not solved by the Bellman-Ford algorithm. And the reason we're not looking at an algorithm for that case is that no one knows an efficient algorithm for that case. So it's an open question whether there is an efficient way to take a graph containing negative cycles and find the shortest path tree, where you define the shortest path as the shortest path that does not use a cycle. If you found an efficient algorithm for that problem, you would become very famous immediately, because it's related to a whole other set of open problems where problems we would like to be able to solve, but no one has found an efficient way to solve them, but no one has proven that they can't be solved. So that involves the theory of NP completeness. We'll talk about that at the end of the semester. Just want to give you a heads up that this is an example of an NP complete problem. The problem of finding shortest paths in the presence of negative cycles, subject to the restriction I mentioned. And it has the property that if you could find an efficient algorithm for this, that would automatically give you an efficient algorithm for a whole host of other problems that people would like to solve. But we'll get to that eventually. For now, we're just going to say no net negative cycles, and for this algorithm here, which is Dijkstra's algorithm, we are going to allow cycles, but we're not going to allow negative edges at all. Right, so let's look at this. The idea behind Dijkstra's algorithm is to grow the shortest path tree incrementally, just like in breadth-first search. So we start at the root. Now in breadth-first search, you would start at A and you would explore all the edges out of A. And then you would be putting the vertices you reached, E, F, and B, onto a Q. And then you'd be expanding from B, let's say, and then from E, and then from F before you looked at anything else. So in Dijkstra's algorithm, we're going to start with our start vertex A. So we're going to grow the tree, so we start with A. During each pass, we are going to add to the tree the non-tree vertex that is closest to the start vertex. So if A is our starting vertex, what would we want to do next? What's the closest vertex to A that's not already in the tree? B, right? The only possibilities are B, E, and F, and B is the closest to A right now. So B would become part of the tree. At that point, A and B are part of the tree, and we got to again choose the vertex that is closest to A, but not in the tree already. So what would that be? It could be E, because E is 3 away, right? What about C? C is not in the tree, and it's 3 hops away. So we could consider C, it's a tie. F is 4 away, so we wouldn't consider it. So that's the game we play. We grow the tree, so we're continually interested in the tree, the fringe, which are the vertices that are adjacent to tree vertices, and then there's the stuff that we're not considering down in the depth. We haven't discovered them yet. So that's the idea. All right, so that's what I just showed you. Let's actually use the animation. So if we start with A, then our yellow is the tree so far, purple is the fringe. Vertices you can reach in one step from a tree vertex. And we decided that the next one we'd want to do would be B. And now the fringe has grown to be E, F, and C. Right? Which edge should we update next? Either that edge from B to C or that edge from A to E. And I choose to do the one from B to C. So we're choosing which edges to update in this fashion. You're choosing the edge that leads to the closest vertex to A that's not already in the tree. So which vertex should we consider next? Which of those purple fringe vertices is closest to A? Okay, it's E. Now, how do we know? The idea is that, I'll ask that question later. So we'll do E. Okay? Now which one? See, F is 4 away, and G is 5 away, D is 4 away. So D comes next. And now we're considering F, G, and H, and it looks like F is closest at 4, and then H is next, and then G. Then we're done. So we're just making one pass through. How do we do that? How do we efficiently, the bottleneck is trying to figure out, when in a situation like this, is trying to figure out which of those purple vertices is closest to A. Right? We don't want to have to do a search from A to find out the distance to F, G, and D. We need to be able to do it efficiently. So that's the gist of the algorithm, is how you efficiently decide which edges to update at which times. And the way that we do that is use a priority queue. So we use a priority queue to keep track of the fringe. And the fringe will be ordered by distance back to A, or the distance from A to it. And we'll always be picking the fringe element that's closest to A. And then as we explore out, we'll be adding things. Okay, so priority queue, I assume you've seen that before, am I right? Talked about that in 2420. So what is well, it says right here, it's a data structure that keeps track of unique keys with associated weights. So the operations are, you'll create a new empty priority queue. And I'm going to assume that we are going to know the size of the priority queue initially. So the maximum size is n. We're going to use it to hold vertices. You got to have some way of determining if the priority queue is empty. There's nothing in it. There's got to be a way to insert a new vertex with a given weight, a new key with a given weight into the queue, or if V is already in the queue, to change the weight. So either insert it or change it if it's already in there. And then we got to be able to do to remove and return the vertex with the smallest weight. So those are our priority queue operations. And subject to those assumptions, to the setup, this is Dijkstra's algorithm. So we're going to stare at it for a minute, and then we'll look at an animation of how it works. But for right now, I just want I've got it side by side with breadth first search, because I want you to see how similar they are. Your book uses a different way of describing priority queues, which is one of the few things, not priority queues, Dijkstra's algorithm, which is one of the few things I don't like about the book. So we're going to go on exams and assignments and everything. We'll go with my priority queue my Dijkstra's algorithm implementation. So what's the difference? The first block's the same, right? Initializing, distance, and previous and such. What's different here? Breadth first search is just using priority queue. We're using a regular queue. And Dijkstra's is using a priority queue. But in both of them, we initialize the priority queue with the start vertex and a distance of 0, or we initialize the queue with S, with the start vertex. We have a loop that you do as long as the data structure is not empty. Breadth first search, we remove the front of the queue. Here, we do a delete min. We go through every edge. And then over there in breadth first search, we do a certain kind of update. What are we doing for each edge here? For each edge, out of U to V. So for each edge out of U, what are we doing in Dijkstra's algorithm? Right here. Yeah, that's the update operation. So you update every edge out, and then you also, when you find a better way to get to V, you've got to go into the queue and change the weight of V in the queue, in the priority queue, because you found a better way to get there. So that's Dijkstra's algorithm. let's look at it a different way. It's a different set of slides, but so I'm transitioning here. Okay, so we're back to the same thing we were looking at. There's Dijkstra's algorithm. Let's see how it works. So there's our graph, no negative edges. It does have a cycle. So the first thing we're going to do is initialize the data structures. So there's our previous and our distance array. The next thing we're going to do is initialize the priority queue, and I'm putting it down here. So right now, our priority queue contains A, which is our fringe to start with, and it has a distance from A of 0. So that's priming the pump. Now we're into the loop. So each time through the loop, we first, as long as the priority queue is not empty, we do a delete min on the priority queue. So what will come out of the priority queue when we do a delete min? A. So I'm going to remove from the queue, and then I'm going to color it yellow in the tree to indicate that it's now incorporated into the tree. All right, now, we've got to, basically, what it says to do is to update every edge out of A. So we look at all the edges out of A, and what's going to happen? I'm going to consider that edge from A to B. All right, does it need to be updated? Is the known distance to B greater than the distance to A plus the 2 on that green edge? Yes. So we're going to update the data structure. So watch what happens. Let's see, B is going to change. So B previous became A, distance became 2, and we threw B onto the queue. We color it purple to indicate it's on the fringe. All right, now we just continue the loop. Now we're going to do A to E. Same thing will happen. We found a better way to E, so we update it. So E will get an entry in the 2 tables, plus it will go on the priority queue. And then the same thing will happen with F. So at that point, we have finished dealing with A, and we will never deal with A again. A will never be updated. Now, clearly you can see that A will never be updated because there are no edges in. Imagine there were. Suppose there were an edge from B back up to A. How do we know that A will never need to be updated again? Even if there's an edge back to it. Yeah. There's no negative edges. That's where the negative assumption comes in. Imagine there was an edge from B to A of weight negative 100. Now that would be a negative cycle. But, all right, let's do it a different way.
A to B with -2?
Yeah, I have to be careful here. A to what?
Or D to A with -2? Or maybe -3, I don't know.
Yeah, let's do it this way. Let's come back to this one. I can't make an example of the root. I'll make an example when I get to a different spot. So what's going to happen now? We've got our fringe on the queue. So the queue is always the fringe. And the yellow, the yellow things, there's nothing in the algorithm that tells you that A is yellow. That's just, I'm putting it there to help us remember. So what's going to come off the queue now? B. So B comes off the queue, and immediately I'm coloring it yellow, meaning we're done with B. B will never change. Now I can talk about the thing. Suppose there were an edge from B. I want to find an edge that would make the distance to B shorter than 2. Without having a negative cycle. I'm having trouble seeing that. Because if I wanted to put an edge from C back to B of weight -2, but that gives us a negative cycle, which is no fair. What did you say? Yeah?
Well, it's really difficult to do from B, but if we were to say, look at it from E's perspective, it'd be really easy to have like a path from A to B to E that's shorter than the A to E path.
Well, in fact, we're going to find that. Because the shortest path is going to be A, B, F, E. Okay, well, I'm making a very good point. But the reason we don't have to worry about ever finding a shorter way to get to B is that there are no negative edges. So if we imagine going from B to some other vertex and then somehow getting back to B. that can't be a shorter path because there are no negative edges along the way to make the thing shorter.
You just look at that cycle with F, C, and G.
The cycle with what?
F, C, and G, and just create like a negative number in there. That doesn't create a negative cycle, but just creating that scenario you're trying to.
Okay, so you want to make one -5?
Something like that.
Okay. But I still don't think that. But I'm floundering here, so I'm going to move on. Okay. Now we just added B to the tree, so we got to consider every edge out, right? So we're going to consider B to C, and what do we know? Currently C has an infinite distance, so that'll update, and C will go onto the Q with a weight of 3, and then we're going to do that edge right there, and that is an edge from to a thing that was already on the fringe. So it's possible you're going to find a shorter way to something on the fringe. You're not going to find a shorter way to something that's yellow. Is that a better way to F?
Yeah.
Okay, so currently the distance to F is 4. We just found one of length 3. And so we're going to update, the F entries in those two arrays are going to change, but also F is going to get a weight of 3 in the priority queue. So there it happens. Okay? I guess I didn't want to animate these things changing position, so we'll just have to eyeball which is the lowest. So we found a better way. That's all the edges out of F. What's coming off next? Either C or F. Okay. Maybe I'll try this one more time. So let's suppose we take F off now. And we go from F and we update E. And they both become yellow. And then later we come to C. Now you might think, maybe this is what you're getting at, if we put a negative 5 right here, after we've committed to F and turned it yellow, it's possible then we could come to here, and here, and here, and find a shorter path to F than we found originally. So we come here and turn this yellow, but it turns out there's a shorter path here. Even though there's not a negative cycle, make that -5. We've got a shorter path to F, but it's already been colored yellow. We don't have to worry about that because you can't have a -5 to do that. So we're guaranteed to never find a shorter path. All right, but I picked C to do next. We're going to consider all the edges out. That one will give us a better way to D, so it goes on the Q. That one, from C to G, gives us a better way to G, and it goes on the Q. And what comes out next will be F. Okay? So we consider F, and we consider that edge from F to C. Now this is again my example. If that happened to be a negative number, that would be a shorter path to C. If it were a big enough negative number, but and we would be updating something that's not even on the priority queue, but that can't happen because no negative edges. Yeah.
Can they be 0?
Yeah, they could be 0, but
Would that be an issue though?
no, because we do greater than, not greater than or equal to when we compare. Okay, so that thing is not going to succeed. Now, suppose I change that. I made that be negative something. What would happen if we now update, if we instead we change the algorithm so that we allowed a negative edge and it passed this test and it put C back on the priority queue? That's what would happen. If you ran this algorithm on negative edges, sometimes you find a shorter path to something you committed to and it would go back onto the queue. What would happen then? What's that? Well, if there was a negative cycle, there'd be an infinite loop. But if it weren't, if the negative edge didn't form a cycle, you would end up, then you'd just reprocess C, you'd update everything out of C, and eventually things would settle down, as long as there's not a net negative cycle. So why do we rule out negative edges? Because actually the algorithm works correctly with negative edges.
It's more work.
Well, he said it's more work. So Dijkstra's algorithm is efficient as long as there are no negative edges. Once you allow negative edges, you get situations where end up updating the same vertices over and over again. And it can become exponential running time. So it still works, but it's grossly inefficient in the worst case. Anyway, that green edge is ignored. And then we look at the edge from F to E, and that's an improvement. So we're going to update E to now have a weight of 4 on the Q. Okay. Now we're going to pull out D, and we'll consider there's only one edge out from D to H, and that's an improvement. Then we pull out, let's see where we were. Oh, we pulled out E. E becomes yellow, but the no edges out. The next thing we pull out is going to be G, and it has that one edge to H, and it didn't improve on things. And finally, we pull this guy out and no edges. And we're done. So, we made a single pass using the Q. It's a lot like breadth first search. The only difference is the order in which we consider the vertices are governed by the priority queue, not by the queue. So it's not first in, first out. It's smallest in, first out. Yeah.
It did have negative edges. Couldn't you just scale everything to be positive and then?
Okay. So here is a question I get all the time. Suppose you had negative edges. Couldn't you just add, say the largest negative edge was negative 10. Couldn't you just add 10 to every edge to make them non-negative, run the algorithm, and then subtract 10 off of every edge? Would that work? Can someone think of a counterexample? Yeah.
There's a negative cycle.
Well, yeah, we're not allowed negative cycles. So. I want a graph. It'll work just to have 3 vertices. I always have a hard time remembering my counterexample, which is one reason I'm asking you. Let's let the start vertex be A. We'll figure out which way to draw the arrows. I want negative weights such that this idea of transforming by adding and making, adding a constant to each edge and making it positive or non-negative and then solving the problem will give you the wrong solution. It won't find the shortest paths. Yeah.
Because if you brought it all to a positive value for them, you would have a different outcome for the fact of, like, let's say if A to B was -1, but then B to C was 2, and then going back was -2, you brought them all up to, let's say 0, it would have a different outcome in the sense of...
Yeah, I want it to find a different tree. So let's try this. Okay, so there's negative edges. There's no negative cycle, so that's not a problem. What's the shortest path from A to C? Well, it's A, B, C. No, it's AC with a -2. Okay? What happens if we add 2 to every edge? So we end up with A to B being 1, to C being 0, and to this being 4. We still get the same answer, right? If we do shortest path algorithm on this, we're going to find the shortest path from A to C is 0, right? Or the shortest path from A to C is just going from A to C. So what I want are some weights so that this transformation doesn't succeed. Yep.
Well, if the A to B edge was -3, and you added 3 to all of them, the shortest path from A to C would be just A to C in the next algorithm?
Okay, so you want me to do...
Not the A to B edge is -3.
Oh, okay. Sorry.
And A to C is still -2.
I wonder if Control Z works here. Yeah. So you want to make this be... I want it erased. Okay. You want to make this -3?
Yeah. Now, if you add 3 to all of them.
Okay, we add 3 to all of them. We get 0, negative, or +1, and 5.
So now the shortest path is A to C
Okay.
instead of A to B to C.
Well, no. This one you just gave me, the shortest path from A to C is negative 2 from A to C directly. So still getting the same solution. So, yeah?
I have an oblique answer to that.
Okay.
So if you compare the weight resulting from A to C or from A to B to C,
Mm-hmm.
you have negative 2 or negative 1 on the left hand side. So they're only 2 apart. But on the right hand side you have 0 plus 5 is 5 and the 1, so you have 4 apart. So there has to be some example somewhere where that scaling makes it
Mm-hmm.
not.
So the root of the problem is that when you add the same amount to each weight, you're penalizing large paths twice. So a path of length 2 is being penalized twice by adding to it, whereas a path of length 1 is only being penalized once. So who has found a way? Yeah.
Could you have them all be like negative 5? Like in your same drawing? So A to B would be negative 5, B to C would be negative 5, and A to C would be negative 5. Then they both turn out to be 0.
So if we did it that way and then added 5, that we're getting closer, because if we added 0 to everything, all these become zeros.
Then you'd have a possible wrong answer, right? Because it's not.
Right. In the original, the shortest path is from A to C, which is negative 10. In the new one, either one will work, so you might possibly get AC, which is wrong. Yeah?
We just take A to C to be negative 6.
Okay. Yep, I think that'll do it. So then what do we have to do? We have to add 6 to everything, so we get a 1, and a 0. Okay? Okay, so that works because in the original graph, the shortest path from A to C is A, B, C, which is negative 10. But when we transform it, the shortest path is directly A to C. So we get the wrong answer when we do that transformation. And again, the problem comes from the fact that this path of length 2, we ended up adding 12 to it. In this path from A to C, we only added 6 to it. So that's it. It kind of skews the. It's not fair in terms of. That's why it doesn't work. It's interesting. This question is asked at this exact time every time I teach this class, and I always panic a little bit because I can't quite remember the counters. Okay, so back to where we were. What remains with Dijkstra's algorithm is a couple things. There's to analyze the complexity. And the complexity is interesting because what we will see is that the complexity of Dijkstra's algorithm depends on the complexity of the priority queue. And it turns out that if you're using adjacency list representation, you want to use one kind of priority queue representation. And if you're using adjacency matrix, you want to use a different kind of priority queue representation, which is really the first example of that we've seen. So we will we'll do that at the beginning of class next time. For now, we're done.